In this section, we will consider vapor-liquid equilibrium. You know that these data are important for the design of several separation techniques. For example, distillation column, which is very old but powerful technique to separate or purify our chemicals. What is the separation means? Separation means, well, we try to separate two things from homogeneous phase, right? So we try to induce a new phase with different composition. Let's say we have a mixture at one phase, right? At single phase. And then we try to separate something out of our original chemicals, our original mixture. So we try to induce a new phase with new composition. Then once new phase occurs and the new phase has new components, then we can separate it out. In this case, let's say we have a mixture in liquid phase. We try to induce the vapor phase contain different composition. Then once we induce vapor phase, we can separate liquid phase and vapor phase out easily. And the vapor phase, it has different components, so we can induce new phase with totally different composition, right? The composition chain. For example, if our mixture contains A and B at certain composition, certain ratio, certain mole fraction, and once we induce a liquid phase, and that liquid phase has different components, different ratio of A and B, then you see that at the equilibrium, our liquid phase has different mole fraction from the original phase. And also we induce vapor phase, and that vapor phase has different mole fraction of A and B. So if we repeat this phenomena, we can purify A or purify B. And if we repeat this process again and again, so A becomes more and more pure, or B becomes more and more pure. What about data that require to design or operate distillation? You know that because we induce a new phase, right, at equilibrium of vapor and liquid. So we want to know the composition at equilibrium, or information as vapor liquid equilibrium. You can perform the experiment in order to obtain this data, like using this system. For example, we have acetone and water, and we control the pressure to be at 1 atm. And you know that the boiling point of pure acetone is at 56.15 degrees Celsius, and if we have pure water, boiling point should be 100 degrees Celsius. But for the mixture contains different ratio of acetone and water, has different boiling point. We can tabulate the data. We can present these data as a table. You see that at first line, this line, the boiling point at 100 degrees Celsius, we know that it must be pure water. So if we present our data in terms of mole fraction of acetone in liquid, it should be 0 because our system contains pure water. Acetone must be 0. And if we look at the composition in the vapor, the mole fraction of acetone in vapor phase must be 0 also, because the system contains pure water. And if we adjust the mole fraction of the acetone in liquid phase to be 0.05, in this equilibrium, the mole fraction of acetone in vapor is 0.6381, and the boiling point of this system is at 74.8 degrees Celsius. You see that if our system contains higher concentration, higher mole fraction of acetone in both liquid phase and vapor phase, so our system contains smaller ratio of water, right? And the boiling point decreasing along this way, right? Because the light component, we have higher fraction of light component, which is acetone. At the final point of this table, we have mole fraction of acetone in liquid phase at 1, right? That means we have pure acetone. And the boiling point is the boiling point of acetone at 1 atm. And this data can be represented in a form of graph. We can plot between x and y, mole fraction of liquid phase, mole fraction of acetone in liquid phase, mole fraction of acetone in vapor phase, with temperature. The mole fraction of acetone in liquid phase is plotted in blue line. It's shown as blue line, while the orange line represents the mole fraction of acetone in vapor phase. By using this data, we can plot a relationship between mole fraction of acetone in liquid phase, or X acetone, and Y acetone, or mole fraction of acetone in vapor phase. Okay, we plot X and Y here, and it's shown as the relationship is shown as blue line here. It is note that the orange lines is just imaginary. We call it operation line. okay, where x equal to y, okay. But our equilibrium follows this line, this blue line. For any mixture, we can perform experiment and present data in form of table or in form of figure, in form of graph like this. But you know that we have some limitation to use this data because while experiment is expensive, one point of data requires one experiment. And you know that while we have data which is discrete in nature, because we cannot continuously adjust everything and get data at every point, right? So if you want to know the equilibrium point which is between these data, we have to perform new experiment, right? Even here or here, between this point, it is important to perform new experiment in order to get data. So it's better if we formulate these data as a model, and we can use this model to predict the relationship between vapor and liquid at some point around this point. Also, with the model, we can extrapolate to the condition. We have no data, we have no experimental data. So basically, the model can be in a empirical form. The most simplest one is k-value, or you can call it k-factor, okay, where we write relationship between y and x. You know, y is mole fraction of I component in vapor phase, and xi represent mole fraction of I component in liquid phase. A ratio between y and x we call it ki. So ki is a ratio of yi and xi. Okay, and using this data, if we determine k of the heavy component and light component, the light component means the component which has higher vapor pressure. Okay, higher pressure means lower boiling point. A ratio between ratio of k factor, k value of light component to the k factor of heavy component, we call it alpha. Okay, so alpha is k of light component divided by k of heavy component. For example, the previous data, we can calculate k. We can calculate k at each composition, okay, each point in the data. For example, at xa is x of acetone is 0.2, x of acetone 0.2 is here, okay. X is 0.2 is in equilibrium with y is 0.7916 here. So we can calculate K of acetone and also K of water, even though the data represents the table shows X and Y of acetone, but we can calculate the X and Y of water, okay, because our system is binary. Then we can calculate alpha here. And if we calculate K of acetone and K of water, and also alpha at each point, each data point, and we shown in this figure, we see that how K evolve at each condition. Though the K factor model is powerful and simple, but it's too simple and it has no connection with the basic theory of thermodynamics. You know that for thermodynamics, previously we derived that, you learned that at equilibrium, fugacity of the same component, let's say component I, fugacity of component I in vapor phase must be equal with fugacity of component I of liquid phase. And fugacity of component I in vapor phase is represented by alpha I YIP. Okay, it's fugacity coefficient, mole fraction, and pressure of the system. And if you look at the fugacity of liquid phase, we know that fugacity of liquid phase can be approximate using fugacity of sat liquid, right? And fugacity of sat liquid can be, well, estimated by, can be approximate as fugacity of sat vapor, okay? And because our system is not pure, our system is a mixture, so fugacity of component I in liquid phase is calculated as gamma I, or activity coefficient, of component I, Xi and Pi, where Pi is a sat vapor of pure component of pure I. Okay, so if we replace this term and this term in our main equation, so we get phi I YIP is gamma I Xi Pi. Well, now we consider the most simplest case where the pressure is low enough to approximate phi I as 1. Okay, you know, at low pressure you can approximate fugacity with pressure, and this is the case. So if phi I is 1, this equation this equation, this expression becomes YIP is gamma I XIPI. Now we work in this model again using the previous data, the data of Weber liquid equilibrium between acetone and water. You see that we can calculate gamma or activity coefficient of acetone and water at each data point. Okay, in order to calculate this activity coefficient, you just rearrange this expression again. So activity coefficients become the ratio between YIP over XIPI. Because our pressure, the pressure of system is 1 atm, always 1 atm, right? You can plug this in main equation. And for PI is a Weber pressure of pure component of I, right? So we know the from this data we know the temperature of the system, right, of the Weber liquid equilibrium. So at each temperature we can calculate the Weber pressure by using Antoine equation. So we can calculate all activity coefficient, the activity coefficient of acetone and water. You see that the activity coefficient of acetone in this system change with mole fraction of acetone in liquid phase. For all point, activity coefficient is greater than 1, and the activity coefficient approach 1. Okay, once acetone reach the mole fraction of acetone reach 1, which means here we have a pure acetone, so the activity coefficient of acetone becomes 1. In the same way, for water, for on range, activity coefficients are greater than 1, and it approaches 1 when our system contains pure water. So now we have our model, Weber liquid equilibrium model. So for this model, we can rearrange our expression, our model, as yi is gamma I XIPI over P, right? And if we assume our mixture, our solution is ideal solution. For ideal solution, gamma I is 1. Okay, so our model becomes yi is XIPI over P, and this model is, previously you know it as Raoult's law. Okay, so basically it originates from we set out Fugacity of component I of Weber phase equals to Fugacity of component I in liquid phase, and we assume that the pressure is low enough, then we can approximate the Fugacity coefficient becomes 1, and more than that, we assume that our solution behave as ideal solution. So we got Raoult's law. Okay, and previously we showed that our system, like, well, for example, acetone and water, gamma or activity coefficients is not 1. It's the activity coefficients for both acetone and water approach to 1 when the system, when the mixture approach pure component. So we see that the system of acetone water is not ideal solution, so we cannot assume gamma to be 1. Okay, for non-ideal solution we need activity coefficient. So our model becomes yi is gamma I xi pi over p. Okay, and this model can be called as modifying Raoult's law, okay, or Raoult's law type activity coefficient. So the next thing we will discuss here, we will consider different types of ideal of solution. The first type we call type 1 is ideal solution behavior. For ideal solution behavior, well, this system, let's say, okay, we have two components A and B. A and B should be, well, similar, very similar. So the interaction between A molecule and A molecule is similar to the behavior or interaction between A and B, and also B and B. Okay, A, we can treat that, we can mention that molecule A sees molecule B and sees molecule A similarly, and at the same way molecule B sees molecule A and see molecule B similarly. Okay, so for type 1 or ideal solution, the activity coefficient becomes 1 for the whole range of mole fraction. Okay, so you see that activity coefficient is 1, right? So the behavior of A and B is similar to the behavior of pure A and pure B. Okay, and if we plot pressure of the Weber pressure of the mixture at different composition, you see that the total pressure is a combination between partial pressure of each component. Okay, for example, this system is a solution of toluene and benzene. Okay, we have toluene and benzene in mixture. Okay, system behave as ideal solution. And if you look at the, well, relationship between mole fraction of benzene in liquid phase and mole fraction of benzene in Weber phase, the equilibrium curve shows like this. Okay, and this line is reference curve or operation line. Okay, and previously I know that, well, you learned from in bachelor that, well, if we have a equilibrium curve like this, it's very simple for the distillation. Okay, if we start from a mixture content, well, different composition, but anyway, you can design the distillation column. Okay, and you know that if you perform distillation of this mixture, finally we get pure A and pure B for sure. Okay, or in this system, pure benzene and pure toluene can be obtained by using distillation technique. Now we plot between the relationship of mole fraction of benzene in liquid phase and vapor phase with temperature. We obtain this relationship. Okay, the lower one, the lower curve, we call it bubble point curve, and the upper one is dew point curve. You see that if we start from here, our solution, okay, with composition of benzene, the mole fraction is 0.5, half of benzene, half of toluene, and we keep pressure constant and we increase the temperature, okay, until it reach this bubble point curve. Our solution, our system reached the bubble point. Okay, the system bubble here, and once the temperature increase to this region, our solution separate into vapor phase and liquid phase. Okay, liquid phase has composition here and vapor phase here. Okay, and it follow the line of each point if we increase the temperature. Okay, until all component becomes pure. No, not become pure, totally evaporate. Okay, no liquid phase left. Then the composition becomes similar to this one because everything's evaporate. Okay, so if we further increase the temperature, okay, the composition becomes similar to the original one because everything totally evaporate. Okay, and you see that in this region, okay, in this temperature range, we induce our solution to separate the phase to liquid phase and vapor phase, and you know the composition of liquid phase and vapor phase at each temperature. Okay, so you can adjust, right? And we obtain vapor phase and liquid phase with having different composition, okay, compared to the original one. Okay, so the second type of solution, we call it positive deviations from ideal solution behavior, or type 2. For type 2, the keyword is positive deviations, right? Why we call it positive deviation? Because if we look at the activity coefficient of component A and component B in the solution, we see that the activity coefficient deviate from the ideal case. Remember that previously we consider the ideal solution, right? Ideal case, the activity coefficients are 1 for the whole range of composition, but here for the whole range of composition, the activity coefficients are greater than 1. Okay, greater than 1. But of course, for pure component, the activity coefficients are 1, right? Okay, so it deviates from 1 to anything greater than 1. Okay, this system is, well, water and isopropanol. Previously we considered water and acetone, right? Water and acetone also, well, show type 2 behavior. So if we have something, a solution with having activity coefficient greater than 1, so you see that the, well, the effect of, what is it, the vapor pressure that of each component in solution is greater than what we can expect in pure component. Okay, and it's true. If you look at this graph where we plot relationship between mole fraction of isopropanol and pressure, you see that total pressure, okay, for the whole range, total pressure are greater than vapor pressure of pure component. Okay, you see that, well, you can imagine that, well, once A and B in the solution, A has a repulsive interaction with B, and because A has repulsive interaction, A has a repulsive interaction with B, B also has repulsive interaction with A also. So, well, A doesn't like B, B also doesn't like A. So A and B try to be, well, A try to keep distance from B, and the best way to keep greater distance between A and B, because A and B doesn't like each other, the best way to keep the distance is they're trying to evaporate, they're trying to be in the vapor phase. Okay, so the behavior, the system show higher pressure because A and B trying to be in the vapor phase instead of in the liquid phase. And if you look X and Y curve or equilibrium curve, we see that our equilibrium curve cross the reference curve somewhere. Okay, for this system, the crossing point is here, right? And you see that reference curve, it's, well, y equals x, right? So we have problem. Why we have problem? Because at this point y equals to x, right? So what is the problem when y equals to x? Remember that for separation we want to induce a new phase with different composition. But here, composition, the mole fraction for liquid phase equals mole fraction of vapor phase. So we cannot induce vapor phase with having different mole fraction at this point. Or you can think that, well, because the behavior of vapor phase and liquid phase is similar, so, well, the behavior of the solution similar to pure component. Okay, so if we start from our solution with this composition, having this composition, and we use distillation column, distillation process to separate it, you know that finally we get, well, pure component here and solution here, because we cannot cross this point, because well, we induce a new phase, right? And new phase has the same composition with the liquid phase always, so we cannot cross this point. Okay, well, what about if we start from solution here, this composition, and we use distillation column? Well, we will get this point pure, and we will stop at this point. We cannot cross this point down here. Okay, and this point is called acetrope. We call it acetrope. Acetrope has behavior similar to pure component. Okay, now we look at bubble point curve and dew point curve. While previously you see that dew point and bubble point will not cross, but here bubble point cross to dew point at this point also. Well, if we have bubble point and dew point at the same temperature, it's a behavior of pure component, right? For this system, for type 2 system, acetrope has lowest bubble point. So we call this type of acetrope as minimum boiling point acetrope. Okay, next time you, well, if you see minimum boiling point acetrope, well, it is a type 2 solution. The next one, the third one. The third one we call negative deviation from ideal solution behavior, or type 3. For type 3, the keyword is negative deviation, right? If we look at activity coefficient, we see that for pure component, of course, activity coefficient become 1, right? Here and here. But for the whole range, the activity coefficients for both components are lesser, smaller than 1. So we call it negative deviation. Okay? And normally we take log of activity coefficient, right? We take log of this thing. Well, log value of activity coefficient becomes negative. That's why we call it negative deviation. So here activity coefficient is, well, less than 1, right? So we can expect the total pressure to be smaller than what we can expect from pure component. You see that for in the solution, total pressure is smaller than we can find in the, well, vapor pressure of pure component. And if we look at the relationship between mole fraction in liquid phase and in vapor phase, we see that equilibrium curve again cross the reference curve somewhere. Okay, but the behavior, it's different from what we found in type 2. Okay, but it forms acetrope anyway because it's cross reference curve, and it imposes the same difficulty for separation using distillation column, because here we cannot cross, we cannot use distillation column to induce new phase with different composition, right? Because composition of in liquid phase, it's similar to what we found in vapor phase, right? We induce vapor phase, but vapor phase has the same composition with liquid phase, so it's useless. And if we look at bubble point and dew point again, it forms the point somewhere here where the temperature, the boiling point, is at the same place as dew point, okay, which is the behavior of pure component. But here you see that the azeotrope has the highest temperature, right? Highest boiling temperature or dew point temperature. We call it maximum boiling point azeotrope in this case. So next time you see maximum boiling point azeotrope solution, it is type 3 solution. And the last one, the fourth one, or type 4, we call it 2 liquid phase or heteroazeotrope. For this system, we can treat it as a type 2 with strong interaction. Remember that for type 2, A doesn't like B, B doesn't like A, right? And it try to, well, stay apart or, well, keep distance. But if the repulsive interaction is greater than what we found in type 2, A and B form 2 liquid phase. Okay, so in this case, for some reason it has 2 liquid phase. Okay, and we can, well, expect for Weber liquid equilibrium. Okay, equilibrium where we have 2 phases of liquid, 2 phases of liquid and 1 phase of Weber. The next topic is Henry's law. You can use Henry's law for, well, to explain the Weber liquid equilibrium. But why we need Henry's law? Well, if we want to study the system where the Weber phase cannot be condensed, for example, Weber liquid equilibrium of water and nitrogen gas. Last time we use this model, right? Modify Raoult's law. And, well, look at PI. What's PI? PI is Weber pressure, right? Weber pressure, set Weber pressure of I component. The problem arises for, well, non-condensable phase because, for example, water and oxygen. For water, it's okay, we can find the set Weber, right? But for oxygen or for nitrogen, we cannot find the set Weber of these components, these species, because, well, so we have problem because we cannot find this information. So to solve this problem, it's very simple. We, instead of PI or set Weber pressure, we use a constant, and we call it Henry constant to represent this term. Okay, so it is like this. Yi is a fraction of xi hi p. Okay, well, you see that we neglect gamma I here. Why we neglect gamma I? Because for Henry laws, well, usually we apply this model to the system where we have, for example, water and oxygen, okay, condensable phase with non-condensable phase. So you see that for non-condensable phase, the concentration is very small, so we can assume that condensable phase component has, well, we can approximate the concentration as a pure component. So for pure component, gamma is equal to 1, okay? So for the model, it's yi is xi hip. So far we have discussed several VLE model, right? Weber liquid equilibrium. Now we're going to apply all these things to calculate some parameters. Well, for binary mixture, if we fit a mixture to the system, okay, to the flash tank, let's say flash tank, single stage Weber liquid equilibrium, and we let it flash, okay, from a Weber phase, a liquid phase, we can model this system, okay, using material balance. What we fit to the system separate into Weber and liquid stream, right? So F equals V plus L, right? Where V is the flow of Weber, L is flow of liquid. Okay, so the next thing is species balance. Okay, we consider component I. We see that for mole fraction, we represent mole fraction of component I in feed stream at Z. So if Zi equals Vyi plus Lxi, okay, this is a balance for component I, species I. Okay, and previously we discussed of the model, right? The relationship between y and I, or y and x. Okay, mole fraction in liquid phase and mole fraction in Weber phase. Okay, you can model it as a using K factor, or you can model it as using modified Raoult's law. It depends. You can use it. You can use modified Raoult's law if our solution is not ideal solution. Okay. And if we use modified Raoult's law, we need activity coefficient model, because we know that activity coefficient model, or activity coefficient, depends on concentration, okay, or mole fraction in liquid phase. We can use one-line equation or other type of activity coefficient model to calculate this activity coefficient model. Okay, what about PI? For PI, or side Weber pressure, you can use Antoine equation to calculate it. So for VLE calculation, we can distinguish the problem into several types. The first type is bubble point calculation. For bubble point calculation, well, consider the problem that we have liquid mixture, a mixture in liquid phase. Okay, and we want to determine a bubble point or dew point. Okay. Oh, sorry, in this case just only bubble point. Okay, we have liquid phase and we want to know the bubble point. Okay, you can specify temperature or pressure. The first case is temperature specified bubble point. Consider the problem that we have a liquid, right? And temperature already specifying that, well, bubble point at this temperature. So we want to determine the pressure, right? And also because we know we have liquid phase, we know the mole fraction of liquid phase, and we want to know mole fraction of Weber phase. Okay, so our unknowns are pressure and Y. Okay, so from this expression, because we know our liquid phase, we know the mole fraction of our liquid phase, right? And because we know Xi, by using activity coefficient model, we can calculate gamma I, or activity coefficient, by using any model, any activity coefficient model. And because temperature already defined, if we know the temperature, we can calculate set Weber pressure of pure component using Alton equation. So we know gamma X and Pi. Okay, gamma I, Xi, Pi. Our unknowns are Yi and P. Okay, so for binary system, we have two equations, right? The same P, but we have Y1 and Y2. Okay, so we have three, right? Three unknowns, but we have two equations. The next equation is Y summation of Yi, okay, or Y1 plus Y2 must be equal to 1, right? So this is the simple case. Okay, so if we have liquid phase first, and then, well, temperature already defined, and we want to find the bubble point, you can calculate it. The next type of calculation is pressure specified bubble point. In this case, we have liquid phase. Again, we have liquid phase, then we know Xi, right? If we know Xi, we can calculate gamma I using activity coefficient model. But we don't know temperature. If we don't know the temperature, we cannot calculate the Pi, or set Weber pressure. Okay, we have to leave it like that as a function of temperature. So in this case, our unknowns are Yi, right? Mole fraction of Weber phase, because we don't know, we want to find it. But P already defined because it's pressure specified bubble point. So we know P. What we don't know is temperature. But temperature doesn't appear here. Temperature is an implicit function of Pi, right? So you have a log P function here. Log P becomes power of 10, right? As a function of temperature. So we have an implicit function of temperature here and yi, right? So we have three unknowns, y1, y2, and temperature again. And we have two equations similar to this one, right? And the third equation is y1 plus y2 is 1. Okay? Then you can calculate bubble point. Find the bubble point. And the next type of calculation, we call it dew point calculation. For dew point calculation, we have Weber. We start from Weber. Okay, we have mixture in Weber phase, and we know mole fraction of component 1, component 2 in Weber phase. We know y1, y2 already. Okay, the first type is temperature specified dew point. Here, temperature already defined. So we look at this equation again. Because temperature already defined, so we know this is explicit function already. We plug in temperature, then we can calculate the set vapor pressure. Okay, our unknowns are P, the first thing, and x1 and x2. Okay, in this case yi already known. So the problem is on xi and gamma I, because xi is our unknown, and we know that gamma activity coefficient is a function of xi, so we have to plug in our activity coefficient model here, which is a function of xi. Okay, so you can calculate xi and pressure of the system. And the next one is dew point calculation, but this time pressure specified dew point. For pressure specified dew point, we know P, right? And because it's dew point, we start from Weber phase, so we know yi already. What we don't know are temperature, right? Temperature is of explicit function here of Pi, and we don't know xi. And because we don't know xi, we don't know gamma I. But we know that gamma I is a function of xi. Okay, so again we have three unknowns, x1, x2, and temperature. We have two equations of these, similar equation here for component 1, component 2, and the next one is, we know that x1 plus x2 must be equal to 1. And the next type of calculation is isothermal flash calculation. For flash calculation, we have information of feed stream. We know Zi. Okay, so we have to apply the whole range of expression here. Okay, so we have to write the VLE, right, as this one, or well, you can use modifying Raoult's law. And we have a components balance here, we have material balance here. Okay, rearrange on this equation, then we can calculate. Okay, again, for this system, for this calculation, we have temperature specifying, pressure specifying. Okay, in this case it's temperature pressure specify flash. Okay, this is the steps for the calculation. And the last type of calculation is adiabatic flash calculation. Previously is flash calculation where we specify temperature and pressure already, but this one is adiabatic. For adiabatic flash calculation, we don't know the temperature. We have to formulate the energy balance equation. We have to calculate entropy, no, not entropy, enthalpy of all components, right? Okay, so we have to formulate the energy balance. Okay, so well, now we discuss again a Tretion K-factor method. For the calculation, well, in ideal solution system, for example, it's for hydrocarbon system, you can use K-factor method for the VLE calculation, where K is a fraction of Y and X, right? And the ratio of Ki was assumed to depend on pressure and temperature and liquid composition. Okay, and remember that if the liquid is an ideal solution, K depends on pressure and temperature, but not liquid composition, right? And for light hydrocarbon system over a range of industrial conditions, liquid phase are close to ideal solution, so it's reasonable to use K-factor method. In Ki as a function of P and T alone. Okay, and we use de Priester correlation to find Ki. De Priester K-factor chart is something similar to this one. Okay, if you know temperature and you know pressure, you draw a line from your specified pressure and temperature. Okay, for example, this point to this point, okay, you draw a line, and if your components, your mixture contain methane and ethylene, well, you can read Ki where the line cross your line here. Okay, then you can calculate, you can find determine the Ki. Alright, and you use Ki for your VLE calculation. Okay, for the step of calculation, well, sometimes we need try and, for example, this example where we estimate bubble point temperature at 200 psi and the dew point composition of liquid mixture of 1.29 mole% methane, 26.5 mole% of ethane, and 72.21 mole% of propane using the Priester K-factor chart. We start from trial T first, and then with given P and T, because P already defined, right? And T is we try it first, and then from this chart we draw a line from P and trial T. Okay, and we read K from each, well, what is it? Methane, ethane, and propane, right? So methane, ethane, and propane. Okay, you draw a line first and then read K factor of methane, ethane, and propane. Okay, and we given Xi. Okay, a liquid mixture here, so we know Xi here. we and ki, we read from the third step, then we can calculate yi, right, using this correlation, this expression. And then we check whether summation of yi calculated from this is equal to 1 or not. If not, well, we back again and try t again. Okay, repeat all these steps until we get summation of yi equals to 1. Okay, so we will stop this section here, this video here.